In Activity 3 in Unit 3, we're going to be looking at the law of conservation of energy. Once again, for some of you, some of these concepts may be reviewed from grade 11. What I want you to take a look at to start with is we've got a 2-kilogram cannonball 10 meters above the earth. Now, it's not moving at this point, so it has no kinetic energy. All it has at this point is potential energy. So I always set up all of our energies that are possible in a system. So I have kinetic energy initial, potential energy initial, that's right here. There's no movement, therefore there's no kinetic energy. I'll cross that out. Just before the ball hits the ground, there's going to be no potential energy final, because if you don't have height, you can't have potential energy. Now what I do is I expand these formulas. At the top, the potential energy is mass, which is 2, times gravity, 9.8, times a height of 10. So what we have here is we've got 98 times 2, which is going to be 196 joules. That's going to be my total energy in the system. Now, energy is conserved in a system. Sorry about that. What that means is that 196 joules has to be consistent throughout. So what you make that equal to is half mv squared. So that means we would double the 196 right there. So we would have 392 joules equals the mass, which is 2v squared. So I would divide 392 by 2 to get back to 196, and I would take the square root of that. Now, I know I'm going through the math pretty quickly here. I'm assuming that you can do the math on these problems. Right now, what I want to do is I want to take the square root of 196, and that's 14 meters per second. Let's go over the main parts of what's happening here. We have a ball that is stationary, and so when that ball is stationary at a height of 10 meters, all we have is potential energy. We do not have kinetic energy. 2 kilograms times your gravitational constant times 10. We have half equals mv squared is our kinetic energy, because that's all we'll have at the end. We will just have that ball moving as we go down. So then what we do is we make that 196, which is our total energy in the system, equal to the kinetic energy at the bottom, and we solve for the velocity. Okay, second problem. What I need you to understand is that we have a scalar measurement here. And what that means is, it means that direction is not important. So we do have kinetic energy at the beginning in this problem. Because it's moving at 5 meters per second, and it doesn't matter what direction it's moving in, we have kinetic energy. So we have to set up half mv squared plus mgh to get our total energy in the system. I always try and get the total energy in the system first. So I go up to the highest height that we are in the problem, and I look at our potential energy and see if we have any kinetic energy. So we've got half, let's say that this weighs 10 kilograms. We've got half times 10 times 5 squared plus 10 times 9.8. Let's say the total height there is 10 meters. Times 10. I'm doing the math pretty quickly here. I've got 25 times 5 is 125 joules, plus I've got 98 times 10, which is 980 joules. That's going to equal the total energy when this car gets to the bottom of the roller coaster. Now, what we don't know is we don't know how fast it's going. But notice that there is potential energy at the end because we have a height. It's 2 meters above the ground. So it's going to be 10 times 9.8 times 2. If you think I'm going a little quickly here and you haven't done this for a while, remember, slow down, stop this, watch it again. So what I'm going to have here is I'm going to have 125 plus 980, which is going to be 1105 joules, equals half mv squared plus 196 joules. What I want to do is move this over so we have all of our energy on one side. So it's going to be 1105 minus 196, and that's going to equal 909 joules. And now we can move through and we can solve for this. So it's going to be 2 times 909, and then we're going to divide that by 10 for the mass, and we're going to get v squared equals 182. We'll take the square root of 182, and we'll get 13.5 meters per second. Folks, the reason I showed the first one is just to show that whatever energy that we start with in the system is the energy we end up with at the end, which allows us to find the velocity. The reason I show the second one is sometimes we're tricked. We do have kinetic energy here, plus we have gravitational energy. If we have movement, doesn't matter what direction it is, we have kinetic energy. And in the end, we still had gravitational energy or potential energy because we were 2 meters off of the ground. Now, the last one, I'm going to let you figure out through the lesson, but what I want to tell you here is they ask a couple of questions, and you're going to see this one in the content. You're going to have a roller coaster situation. It's going to ask you where the roller coaster is going the fastest. Well, it's going to be going the fastest where you have the greatest difference in height. So you'll have the most transformation of potential energy down to kinetic energy at A. But at B, what it's going to say is you're stopping. So what you're going to have is you're going to have kinetic energy initial, plus you're going to have potential energy initial. We're going to cross out the kinetic energy because it is not moving at the end. But what it is going to be saying, or sorry, it's not moving at the beginning. So initially this is not moving, so you can cross out EKI. Now, what you are going to have is EKF plus EPF, so that's kinetic energy final, it's going to be moving. You're going to have potential energy because it's off the ground, but it's going to ask you about braking. Whenever they talk about braking, what you're going to talk about there is ETH, so that's thermal energy. So that is going to be equal to force of friction times the distance it takes to stop. Okay, so this is going to be important that you put force of friction in there. You will always need an angle in there also. Okay, now remember, force of friction, if you need to, you can expand out to mu times force normal. So you're going to have to keep all this in mind as you're working through this problem. I would highly suggest that you understand the following concepts. Once you find the total energy in the system, which is going to be your potential energy plus your kinetic energy initial, you're going to have that same amount of energy at the end. Cross out anything that you know is going to be zero. The reason we could cross this out is there was no movement initially. The reason we can cross this out is because we're just above the ground, so we have no height. The next thing I'm going to suggest that you understand is that if you have any movement in the beginning, you've got kinetic energy. If you have any height at the end, you've got potential final. The last thing I would tell you to understand, and this one I'm going to try and get you to understand through doing the content, you're on content 2, is the whole idea of energy thermal. Whenever you're braking, this is the formula that you're going to use right here. Don't forget, when you are done this section, you have an activity to do, U3A3 activity. Don't forget to do this, please.